All right, hi everyone. I'm super glad to be here. Today I'm going to present discriminator-guided chain of thought reasoning. Let's go with a bit of an outline of what we're going to go through today. We're going to introduce chain of thought reasoning with LLMs. We're going to try to find out why language models make reasoning mistakes. And then we're going to discuss some post hoc methods that people have been using to improve reasoning. We're going to introduce guided decoding for reasoning, dubbed GRACE, which is our approach. We're going to go through some results and analysis. We're going to connect this to recent search-based techniques to advanced language model reasoning. And then we're going to discuss some limitations of existing techniques, including ours, and next steps that we think people should start looking into. So feel free to interrupt with questions. I know this is like more of an interactive presentation, so I would be really happy to discuss things midway my presentation. So why reasoning is actually an important thing. And before we delve into this, we first need to define what reasoning is. And this is not an easy task because I don't think there is a consensus upon what reasoning is. But there's a definition I really like from a book called How We Reason, and that is the ability to construct models from perception, description, and knowledge to formulate novel but parsimonious conclusions from these models. And we can all argue that complex reasoning is a hallmark of human intelligence. And we reason about almost everything. So from grocery shopping to planning a vacation, so reasoning permeates our lives significantly. And we cannot expect to reach AGI without solving reasoning. We cannot expect to have a model that represents some levels of AGI without it being able to reason about different problems and different situations. So our scope of this talk will focus on a slightly narrow scope of reasoning tasks, where the input and output are in natural language, and there's a single correct final answer for each given input. And surprisingly, there's many reasoning problems that fall under this scope. Mathematical reasoning, math word problem solving, for example, arithmetic reasoning, symbolic reasoning, puzzle solving, and gameplay. So although this might seem like a narrow scope, but there's actually a lot of different problems that fall under this. And I feel that this has been the focus of most of reasoning with LMs. In the past 2 years, people have been focusing on these kind of tasks. And one could argue that this is some sort of a limitation. Why don't we move to more complex tasks or tasks that do not necessarily fall under this scope? But this is definitely a discussion for another time. So yes, these are the kind of tasks we're going to be focusing on for this talk. So let's talk a little bit about few-shot reasoning. And originally, language models were shown to struggle with few-shot reasoning. So they could not even solve tasks as simple as in-digit addition or math problem solving in a single pass. So for example, you would take a language model, you give it a question, you give it a few-shot prompt, a question and answer, and then a question you want to answer, and then it will give you an incorrect final answer. Same with different tasks like addition and so forth. And the trick was to improve this or to solve this somehow, but it was simple. Basically, allow the language model to reason step by step. So you can either prompt the language model or fine-tune it with what people refer to as a chain of thought solutions. So to give a concrete example, standard prompting would involve giving the language model a question and the final answer. With chain of thought prompting, you give the language model the question and then a series of steps or a scratch pad of some sort, where the language model will be able to reach the final answer this way by reasoning step by step. And this has shown to dramatically improve performance on a lot of tasks because the language model, again, was able to reason step by step as opposed to just outputting the final answer right away. Now, the question here is why does chain of thought help? And this is a bit off track, but it's something that I've been personally very interested in, and a question that I feel that is not answered clearly yet. Why does chain of thought reasoning, why does chain of thought prompting or chain of thought reasoning improve the reasoning performance? And I would argue that there's a few possibilities for this. Maybe it allows to spend extra computation per problem. And there's been some recent work that showed that training language models with pulse tokens, where you basically allow the language model to spend extra compute, can help. Maybe it decomposes the input problem into easier subproblems. So you can think of each step as solving a separate subproblem with the goal of solving the final problem at the end. Maybe it serves as a working memory for the language model, because language model does not have to store these intermediate variables internally. So it can just attend to the generated context. So it doesn't have to memorize these. And maybe it's a combination of all of these. But I feel that right now in the community, in the literature, we lack an understanding of why chain of thought reasoning helps. And this is definitely something that I feel is worth exploring. So before we talk about a reasoning being correct or not, I feel it's important to define what we mean by correctness here. And interestingly, there has been a lot of work showing that language models could reach a correct final answer, but the intermediate reasoning itself is wrong. To give an example, maybe you have a question like this, and Flantify was able to reach the correct answer, but there's an intermediate step that says 2 weeks in a month. So there's 2 weeks in a month. And these examples have been shown also on a higher level, like on much larger models like GPT. So while chain of thought exposes the model reasoning and allows us to verify its correctness, it's important to not just look at the final answer, but also look at the intermediate reasoning. So for the purpose of this talk and for the purpose of this work, we're going to say that a model has reasoned correctly or that a solution is correct if, first of all, each of the intermediate steps does not include errors like logical, factual, or computational errors, etc., and the final answer is correct. So we're not just looking at the final answer, we're also going to look into the intermediate steps themselves. This is not a formal definition, but should do for our purposes here. So language models still produce incorrect steps along the chain of reasoning. And it's important to ask why such reasoning errors happen. And we argue that this is an artifact of both training and inference. So when it comes to inference, people usually use common decoding strategies, like greedy or beam search. And these strategies typically optimize for the sequence likelihood. They're trying to find a sequence of maximal likelihood according to the language model. But the problem is that language models can be very poorly calibrated when it comes to reasoning correctness. First of all, they trained on internet data to predict the next word. And the training objective, first of all, the data itself can be of low quality, so it can include a lot of incorrect reasonings. And also the next word training objective does not model the correctness of the next token in any way. So language models are poorly calibrated, and this results in them assigning high probability to incorrect reasoning. So typically, when you look into a potential candidate next steps when you're generating a chain of thought, in the many cases, you'll find that the most probable, the most likely reasoning step according to the language model is not necessarily going to be the correct one. So language models can assign high probability to incorrect steps and vice versa. And again, decoding chain of thought solutions with standard decoding strategies will produce incorrect chains. And to drive this point home, we can look at an example of a question from GSM8K. And we take a language model like Llama 13B, and we're going to do chain of thought prompting to that model. And let's say the language model has already produced a correct step, we refer to as a prefix, that is correct. But then we can look into the candidate next steps following this step and rank them based on the length normalized average token probability. Interestingly, you're going to find that the most likely reasoning steps are actually incorrect. They are not going to lead to the correct answer. And the answer that is and the step that is correct has much lower, significantly lower average token probability compared to the other ones. So basically, incorrect steps are assigned higher average token probability than correct one. And so if you're using standard decoding strategies to decode next steps, you will likely fall into errors. There's been work on what is referred to as post hoc methods. You basically try to sample multiple full reasoning chains and then rank them based on correctness. This has been shown to improve performance a lot. And there are two main techniques that I'm going to focus on here, self-consistency and verifiers. And they differ mainly in their ranking criterion. How do they rank these sample chains? Um, for self-consistency, uses the final answer frequency. So basically, chains with more frequent answers are more likely to be correct. Verifiers, on the other hand, they use a notion of chain correctness. So they basically train a model to differentiate correct and incorrect chains based on the final answer, and then use that model at inference time to rank sample chains based on correctness. There are two main issues with post hoc methods. First of all, they still rely on sampling from the underlying miscalibrated language model distribution. So basically, these models sample full chains using random sampling from the language model. And so they're still relying on this miscalibrated distribution. And the other issue is that they have no control over the decoding process. So they're applied over full chains and after the decoding has already finished. So you need to sample full chain and then apply these post hoc methods on it, as opposed to intervening into the decoding process, which is what we're going to try to do. So this is an example from self-consistency paper, and you can see that first of all, you sample full chains here, then you look at the final answer, then you see the most frequent answer and use it as your solution. So these two issues make these post hoc approaches still likely to make mistakes and also very highly sample inefficient because you need many samples to run into correct chains. And we're gonna touch into this again and at the end of towards the end of the presentation. But basically, because you're relying on random sampling, you need a lot of samples to be able to run into correct chains. So we argue that guided decoding can help, and we propose guided stepwise decoding to address issues with post hoc methods. So what we mean by guided is that we're going to recalibrate step scores based on correctness. So we're going to take step likelihoods from the language model and then recalibrate them based on correctness, how correct they are. And when we say stepwise, we mean that we're going to exert finer grained control at the step rather than at the chain level. So we are actually intervening into the decoding process and guiding it at the step level. To make this clear, on the left here, this is what post hoc approaches do. So basically, they rely on random sampling, then until you have a full chain, until you've reached the final answer, then you apply a verifier or self-consistency on the top. With guided stepwise decoding, you are performing stepwise guidance. So basically, you sample a step, and as you sample a step, using some sort of a guider model to guide you towards more correct step. So let's formalize this a little bit. Given a problem Q and a correct solution prefix, S1 until ST minus 1, let's assume access to some discriminator model, D, that outputs a real valid score, D of Q and S1 to T minus 1 and ST. And this score is basically an indicator of how correct is the step ST with respect to both the prefix and the question. And let C be a binary variable indicating the correctness of the generated step. And so typically we want to sample a next step, ST, conditioned on the prefix we have, conditioned on the question, and also conditioned on C, or conditioned on being correct. So we can write the probability of next step this way using just Bayes' rule. And then we can just drop the denominator. And then we can replace the probability of a next step by the probability from the language model. So probability of ST, given the question and the prefix, we just replace it by the probability coming from the language model, and multiplied by the probability of correctness, probability of being correct, giving the full solution and the question. Then we know that probability of being correct is proportional to the exponent of exponential of d of question and prefix and current step. Because based on our definition of the score, it measures the correctness of the step ST. And since we know that the prefix is correct, then the correctness of the whole solution will just depend on the correctness of ST. So basically, we can just say that the probability of next step giving the prefix, giving being correct, and giving the question will be proportional to the product of these two terms. Probability of the next step according to the language model. This is the probability without modeling correctness. We don't touch on correctness here, and multiplied by the probability of being correct, or a score indicating being correct, which is basically the exponential of the discriminator score. Question, the discriminator takes as input the question, the prefix, and the current step, and gives you that correctness score. Is that clear to everyone?
But you want to choose an ST, you don't know which one it is. So at the step where you need a probability from your language model, which one would you do? At the step where it says PLM.
This one?
The one above. Oh yeah, it's the same. Which ST would you just try all the STs?
Oh, so basically, this is assuming you have some SD and you want to basically assign a ranking to it or a score to it. So what we do is practically we sample candidate next steps and then we rank them based on this score.
I see. So you have a small, you're not ranking through all the possible tokens.
Yeah, because that would be definitely infeasible.
I
So
see.
yeah.
So you sample top, let's say 5, and then you time it with the second component P, and then the 5 would change. Like the number 5 maybe become number 1 because the discriminator tells it. Says
Exactly.
something.
Exactly. Yes.
Cool.
But the main takeaway from here is that if you want to model correctness into when you're ranking steps, you'll have to deal with two quantities. One is the probability from the language model, the original score that standard decoding strategies use, and then the other is the correctness score, which is going to be like our focus, like what we introduced basically to recalibrate these scores. So basically, a step that is highly likely but is assigned a lower correctness score will be ranked much lower than a one that is maybe slightly less likely but is more correct, and so forth.
Someone also had a question of how do you select a candidate? Is it just the most likely ones from the LLM?
We're gonna talk about this in the next slide. How do you select the candidates and how do we sample them and everything? Any other questions in the chat? Yes, you.
I guess you'll talk about it, but how do you obtain the discriminator model?
Oh yeah, for sure. Yeah, for sure. All right, so let's talk. Let's discuss how Grace decoding operates. So at each time step, we're gonna sample a set of J candidate next steps from the language model. And the way we sample here is just a hyperparameter. Maybe you could rely on top P sampling, top K sampling, or whatever. We didn't really find it to matter much when it comes to downstream performance. Then you're going to score each step using this formula. And here we introduced a hyperparameter beta that determines the contribution of the discriminator score to the overall step score. So the larger the beta, the more your discriminator score is used to recalibrate. The more it's contributing to the overall score. And then we're going to select the top scored step and repeat. And this is basically a greedy approach. And one could argue that why don't you apply beam search? Why don't you apply even tree search and so forth? But for efficiency reasons, we apply just greedy decoding to select the most probable one. But of course, this could be extended to other things. So to make this clear, we have, let's say we have a test question here. We basically feed the language model the question, sample a pool of candidate next steps from the language model. Then we give these to the discriminator model to score each of them, then rank them based on the interpolation between the discriminator score and the language model probability. Select the top scored step, append it to your solution prefix, and repeat and so forth until you have reached a final answer. So the big part here, how do we learn this kind of discriminator? And typically we want D of QR and ST to be high for correct steps and to be low for incorrect steps. R here is a prefix just for brevity. So how do we learn it? And the goal is to obtain a model where giving two steps, giving question and prefix, and two steps, it will give higher score to a correct step than an incorrect step. So basically, our discriminator giving question prefix and some step, and a question prefix and another step, hopefully the score will be higher than it is for the incorrect step. So if we have pairwise examples of the form question prefix, positive step, and negative step, we can easily train the discriminator with some sort of a contrastive objective. And so we can, for example, use a max margin objective like that. And the question here is, how do we get these pairwise examples? And one obvious question is, let's do human annotation. So this is something that a lot of recent work has been trying to do. So there's a paper by OpenAI, let's verify step by step. They just asked human annotators to annotate solutions generated by the model at the step level, whether the step is correct or not, and so forth. But this is very expensive and takes time too. So the question we ask here is, can we leverage gold chains? If you have a solution you know that is correct, how can you leverage it to obtain these kind of pairwise examples? And what we propose to do is an automatic alignment of incorrect chains with gold chains to extract pairwise examples. So how does this alignment look like? So given an incorrect chain and a gold chain, we want to find a minimum cost alignment between the two. And the cost here will be measured by cosine distance, the sum of the cosine distances between aligned steps. And we measure this using Roscoe, which is a model trained to align. Basically, it's trained as a sentence encoder for reasoning steps. And we have found this to work better than using traditional sentence embeddings model. So we use dynamic programming via the Needleman-Wunsch algorithm to obtain such form of alignment. And this algorithm has been used in bioinformatics to align different sequences, but we just adapted here to align steps instead of characters. So let's work through an example of how this alignment works. So given a question from GSM-8K, for example, we have our sampled incorrect chain from the model, and we have a gold chain that we know to be correct. Now, our alignment algorithm will produce something like this, where steps from the incorrect chain will be aligned to steps from the gold chain. And typically, this will result in 3 different types of steps. You're either going to have a comparable step or a missing step, where a comparable step where basically a step from the incorrect chain is aligned to another step from the gold chain. A missing step is where a step from the gold chain doesn't have a corresponding step in the incorrect chain, while extra step is a step from the incorrect chain doesn't have a corresponding step in the gold chain. So we focus on the comparable steps here. And for comparable steps, we just compare the intermediate variables. So in this case, we're going to compare 2,000 grams to 2,000 grams. And since they match, then we know the step to be correct. The more interesting case is where the intermediate variables do not match. So for example, on this step here, 20 does not match 2. So what we do is we basically can use this information to create an example for the discriminator. And this is done by basically treating this step as S negative, treating the corresponding step as S positive, treating the solution generated before or the prefix of the gold chain as our prefix R, and then just create a training example for the discriminator. We do this over many and many sampled incorrect chains to collect examples to train a discriminator. Our algorithm also takes into account the missing and extra steps. I'm not going to get into details about these here, but you can also leverage information about missing and extra steps to further curate more examples for your discriminator training. Any questions so far?
In the chat, we were discussing what do you mean by step, but I think we figured out that looks like each line of reasoning, each sentence.
Yes, there's really no definition of what a step is, but for the sake of this work, yes, we treat each sentence as a separate step. Um, but for practically, we use some sort of a step delimiter to make sure that when we're sampling candidate steps, we're gonna actually stop after we have finished the step. So just to make sure that we are operating at a step level rather than maybe 2 or 3 steps level.
Cool. We have a raised hand.
I, is there a standard way to create steps for chain of thought using, or is this the same way every time? And most like for prompting, I guess.
Uh, I'm sorry, I didn't get the question. Could you repeat?
Yeah. For creating steps,
Hmm.
does this happen in a similar way every time for across like I guess all methods? Or are there other methods for creating steps where it would be like smaller than like a sentence or
Oh, I see. I see what you mean.
yeah.
Um, Usually a step is like it's usually treated as a I don't know, a coherent sentence of some sort, where like something that it's usually a sentence to be honest. Um, but again, it really depends on your prompt. So if your prompt is more like maybe your prompt is like counts 2 steps as a step. Maybe like for example, it merges two sentences into a single sentence via comma or something. Then your model will likely exhibit the same behavior, and so your steps will include maybe 2 sentences and so forth. So it's tricky to define what a step here is, but for the sake of this, we're just treating it as a single sentence that just conveys some computational step, and that's it. Um,
Thanks.
Could you explain again how you get the alternate steps, like the incorrect ones? How do you sample those?
We just sample them using standard like top case sampling. So give the model the
Hmm.
question and some few shot prompts, and you just sample candidate solutions uh,
And
over.
and anything that's not literally identical to the gold step is considered incorrect.
That's a great point. We treat steps that have incorrect final answer as incorrect. So we
Mm.
look at the final answer. If it doesn't match the goal final answer, then we add this to our batch. Sometimes, of course, the language model will give you a correct solution of some sort, or at least a correct final answer. So we just throw these away to make sure that we're only working with incorrect chains. Does that make
But
sense?
what if an early step is correct and only later it goes off course and the final answer is incorrect, but then an early step could still be a correct one, and so you would treat that as an incorrect step
Oh,
mistakenly.
no. If the final answer is incorrect, but there's a step that is correct at the beginning, then our alignment algorithm will catch that. So
Mm.
here's an example of this. Like this step is correct, right? But the
Okay,
final
okay.
answer,
I
the
see.
decision,
Oh, I see. I see. Okay.
yeah.
All
I
right.
have a question, maybe kind of generally based off that. The Needleman wrench generally prefers linear alignment, so minimal differences between, in this case, reasoning values to try to force the Levenshtein distance. I was wondering what happens if the reasoning is maybe backwards, if people are thinking in the opposite order, but they're still able to arrive at the same conclusion.
Yeah, this is a great point. And this is one limitation of this algorithm that is it's not order invariant. So if the steps come in different order than what is in the gold chain, some of these steps will be treated as incorrect. And this is something I will talk about in the limitations later. But yeah, thank
Okay,
you for
perfect.
that. Yeah.
Thanks.
All right, let's move on. Thank you for the questions. Very interesting.
We
Uh,
have your raised hand though, if
oh
you
yeah, okay.
want to ask your question.
Yeah, where's the gold chain coming from?
From just the training data, we have for each of these tasks we deal with, there is a human annotated solution, gold solution that we use.
So the humans not just have to annotate the answers like prompt and the answer. They also have to go through each reasoning step and basically verify all of them, right?
No. So for each of these questions that we deal with, we have just one single gold chain, a solution that we know that is correct, with the intermediate steps being correct. So humans only have to annotate a single solution for each, have to
Yeah.
write down a gold solution for each question.
I understand, but they basically they have to either write themselves down or annotate if you have like a sampled correct answer, right? They'll have to annotate the entire chain of reasoning. You basically
No.
don't.
No, for incorrect, if you have an incorrect chain, like the one on the right, then no humans are included and involved at all. We just rely on our alignment algorithm to obtain the training examples.
Yeah, okay. I might be asking the question in the wrong way. Please continue.
All right.
Can I follow on that? I guess the issue is that you can arrive at the correct final answer with an incorrect chain of reasoning. So I think he was asking whether it's safe to do that without the human actually annotating all the steps in there. So you could have kind of those kind of errors creeping in.
In the goal set, exactly. That's what I was asking about.
Oh, in the gold. No, the gold chains are like they're just, I think they're verified by humans, so we know that each of the intermediate steps are correct and the final answer is definitely correct. So we didn't have to worry about that, at least for the tasks we're working with. But
Okay.
I understand this could be an issue for any kind of different annotation.
Right. I think he was asking whether you would you seem to be answering that they verified the final answer, and he was challenging whether they verified each of the steps as well in the gold chain.
Oh yeah, each of the steps, the individual steps are verified in the gold chain.
Okay, okay. That's I think
Yeah.
that was the confusion.
Oh, I
Yeah,
thought
thank
you
you.
meant,
That was exactly it.
oh yeah, I thought you meant in the incorrect chain. So sorry about that. No, the gold chain, each of the steps are verified. Yes.
Okay, thank you.
Yeah, you're welcome.
There's also a question in the chat asking, so why do we need this alignment? And this alignment algorithm, why do we need it?
We need this alignment because we want to train our discriminator over a sequence of question, prefix, correct step, and incorrect step. And the question is, you do not have labels at the step level. So you want to curate labels at the step level. And that's why we need this alignment algorithm. The other route you could take is human annotation. You generate a lot of solutions from your model, and then you ask humans to annotate them at the step level by assigning a binary value to each step, correct versus incorrect, and so forth. So this alignment is just an automatic way to obtain these discriminator training examples.
To obtain like fine-grained labels per
Exactly.
step.
Exactly. Perfect. So to sum it up, how do we train our discriminator is done in 3 steps. Sampling, we try to sample from the language model to simulate mistakes the language model is likely to make during inference. So we sample a lot of solutions from this language model, giving some questions. Then we do the step alignment or the chain alignment that we just described. We align steps of incorrect solutions with reference steps or goal steps to create contrastive examples. So after we sample, we filter away the solutions with correct final answer because we only want to focus on incorrect solutions. Then we do the alignment as I described. Then last step is training or learning, where we train a discriminator with max margin loss over the curated examples. So we basically train to push up the score of the correct steps and push down the scores of incorrect steps. And I'm pretty sure some of you have thought of RLHF model training here because this process is very similar to how reward models are trained for RLHF. Let's talk a little bit about the experimental setup. As backbone models, we use Flanty 5, Llama 7, and 13B. As baselines, we use greedy compared to greedy language model only scoring, where we're setting beta equal to 0. So basically that means we're only relying on the probability from the language model to score the next steps. We also compare to vanilla self-consistency and verifiers, post hoc approaches we talked about. For each task, we roughly sample 100K incorrect solutions to curate examples for the discriminator training. As a discriminator, we just use a T5 larger encoder, which is about 20 and 38 times smaller than Llama 7 and 13B. And this is something we're going to touch on also later. So as for tasks, we evaluated on 6 different multi-step reasoning tasks, 4 math tasks, and 2 symbolic tasks from Big Bench Hard. Let's see the effect of final answer of our approach. And again, here we're comparing to all these baselines. And we first of all observe that Grace is outperforming almost all baselines and when it comes to final answer accuracy. Now, we can further combine Grace with self-consistency by basically sampling solutions using our guided decoding and then applying self-consistency on the top. And this outperforms all methods across the board. And this also shows the value of guided compared to random sampling. Now, again, we know that the final answer accuracy doesn't tell the full story because the language model could still reach the final answer, correct final answer, via incorrect reasoning. And so we evaluate whether Grace will improve the correctness of the generated reasoning chains. And for that, we use prefix correctness. We measure prefix correctness using ChatGPT. And we also measure trace error, which is a percentage of correct solutions with at least one major mistake. We measure this via humans and also ChatGPT. So we're comparing here to greedy decoding and vanilla self-consistency. And we first of all observe that Grace will improve the prefix correctness compared to greedy decoding by around 7 points, and compared to self-consistency by around 3.8 points. And also it's improving the trace error from reducing it from 9 to 5, which is by about 44% compared to greedy decoding. So we're not just improving the final answer accuracy, we're also improving the intermediate reasoning correctness, which is ultimately what we also care about. Now, we discussed earlier that post hoc approaches require plenty of samples to reach correct answers because they rely on random sampling of full solutions. We compared guided sampling plus self-consistency to random sampling plus self-consistency in terms of sampling efficiency. So we, on the x-axis is the number of samples, and on the y-axis is the accuracy, final answer accuracy. And we can see that we can reach substantially better accuracy with significantly fewer samples compared to vanilla self-consistency with random sampling. So this again shows that we're also improving the sample efficiency of reasoning. Now, we also want to see how the effect of this beta variable coefficient, how this beta coefficient affects the final answer accuracy. And so what we do is we vary this beta, and beta equals 0 means your discriminator is not into effect. We're just calibrating, or we're just selecting steps based on their language model probabilities. And as beta increases, the contribution of the discriminator also increases. And interestingly, we see that as we increase beta, there's a trend where the performance improves, but there's a point where actually performance may drop a little bit as beta goes to 1 or closer to 1. And this shows that we still want to incorporate the language model probability. And this somehow represents the language model learned reasoning abilities. So you don't want to fully abandon these. You still want to rely on them to some extent while incorporating your correctness score from the discriminator, as opposed to just sample and rank, where you just sample and then rank them based fully on the correctness. So you still want to incorporate your language model probabilities here. So the main takeaway is that language models can easily assign high likelihood to incorrect reasoning. We can mitigate this by somehow recalibrating reasoning step likelihoods based on correctness. Guided reasoning can improve both sample efficiency and correctness of reasoning. And interestingly, also a small but specialized model can provide guidance for a much larger model. So again, our discriminator was like 38 times smaller than Llama 13B, but because it was trained specially to detect reasoning errors, it was still able to provide guidance for a much larger model. And this is the direction I'm personally very excited about, the idea of augmenting language models with language models, where you basically have maybe a more specialized language model helping a more general language model with specific tasks and so forth. And this is an example of that. There's plenty of recent approaches on applying search methods on top of LLMs. And a search method is typically used to traverse the solution space, guided by some scoring function or reward. There's been a lot of focus on that in the past year or so. And I would argue that there's three main dimensions to inference time techniques. When you're designing an inference time technique for reasoning, you typically want to look into three aspects. First one is how are you going to score a step or an action or a reasoning step. And this could be a learned method. Like in our case, we'll learn a discriminator specifically for that. It could be prompting. So you could maybe prompt the language model itself to provide some sort of a score for a potential step. There's also the number of parallel chains that you're exploring. In our case, we only explored one chain at a time. Maybe you could explore more. Maybe you could look into a tree or an even graph of thoughts, if you will. The search algorithm used to traverse the search space. In our case, we used greedy, which was simple and more efficient, but one could also think about more advanced techniques like A-star or MCTS and so forth. And there has been a lot of work that is exploring all these different dimensions. Now, when it comes to limitations, I feel that inference time techniques, they're good in that you don't have to train your language model at all, but still there's some limitations. And the most obvious one is latency. The search process could make inference extremely slow. You also, if you're working with proprietary LLMs, you're going to end up doing a lot of API calls if you're using prompting-based scoring functions, because you have to prompt the language model to score each action or each reasoning step and so forth. Our approach requires access to correct chains to train the discriminator. So we assume each question is associated with at least one gold chain, and this may not be available for different tasks. Inference time methods are upper bounded by the performance of the underlying language model. So for example, in our case, we sample a few steps and then rank them. But if all of the sampled steps are incorrect, then there's not much you can do. So even if you have the best discriminator in the world, but your candidate steps are incorrect, all of them, then there's not much you can do. So you're still somehow upper bounded by the performance of the candidate, but by how good the candidate next steps or next actions are. The alignment algorithm we developed is sensitive to the step order, and this was brought by some of the audience here. Yes, so basically we assume that the order is important, but for some reasoning task, maybe you could arrive to the same conclusion with different paths. And so our alignment algorithm will treat some of these as incorrect steps, even though they may not be incorrect. So this is something that we identify as a limitation of the Needleman-Wunsch algorithm, which we use for alignment, and is definitely an area for future work. So what's next? Maybe using the learned scoring function, the discriminator, to train the language model, similar to RLAIF, what RLAIF does. Improving the search efficiency, again, requires many API calls. So maybe there's ways we could explore how to improve this sort of aspect by reducing the API calls, maybe learning from search, which is something I'm personally excited about, where you can potentially learn from the search process and then distill it into some model for efficiency. Maybe training a low-shot discriminator, because again, our discriminator needs these gold chains, and I think it might be very useful if we could obtain a discriminator without relying on gold chains, so maybe relying only on a few such gold chains. But I still think that training a dedicated scoring function is relevant, and there is very recent work that shows language models fail at identifying their own errors. And so I'd still argue that we might need some external specialized model that is just good at detecting errors, and it's like somehow communicating with the language model and giving it feedback, or giving it identifying its own errors, and giving it some feedback so the language model can adapt to that. So I still think this is a very interesting direction, and I'm personally very excited about it. Introducing step order invariance to the alignment to solve the issue that we just talked about. And please reach out if you want to discuss more, if you're interested in Grace, or you want to, if you have some ideas or anything. I'm definitely open to more discussion on this. So yeah, thank you so much.
Thank you. Before we start the Q&A, just a quick time check. Do you have to go at the hour, or can you stay a bit longer?
I can stay until 2:15.
Your time? What is?
Oh, like
15
15 more minutes.
after.
Yes.
I think, okay, let's like not go over too much, but at least we know we can accommodate more questions if there are. I think I'll stop recording for people. Feel freer to ask questions if you think that's okay.
Yeah, perfect.
Okay. For those who are watching this YouTube, know that next time you have to join live to get this part. And bye for now.